Ground penetrating radar. It's time to talk about this technology and compare it to LiDAR, which you may have heard about through a new book, a book that's been out for a while, called The Lost City of the Monkey Gods. So anyway, ground penetrating radar technology and use primarily in archaeology. This talk will cover 4 areas: comparison to LiDAR, a discussion of the basics of ground penetrating radar, and then archaeology, and then a couple of uses for ground penetrating radar beyond archaeology that are brand new. So first, we'll look at LiDAR. 2 different technologies. LiDAR stands for light detection and ranging. Radar, as in ground penetrating radar, stands for radio detection and ranging. So the light frequency using lasers is the primary basis of LiDAR. I took this from the internet. It shows the electromagnetic spectrum across the top. The 2 blue areas that I've highlighted here is the area that LiDAR uses, which is the visible light range with a little bit of ultraviolet and a little bit of infrared, depending on the laser used. And over here is the range used by Gpr in the electromagnetic spectrum. So it's in the FM and TV range, as you can see. Down at the bottom here, I've noted that the Gpr wavelength is 1,000,000 times longer than LiDAR wavelengths. So with LiDAR, it does not penetrate anything solid. What it does do through post-processing is remove jungle, foliage, vines, weeds, grass, trees, through post-processing process called backscatter. So all that's really doing is looking at the ground with the foliage removed. It cannot penetrate stone, earth, or virtually anything, just as your eyes can't see into anything. Gpr, on the other hand, can in fact penetrate ground, as we'll show you as we go along. Okay, ground penetrating radar. It's a non-destructive inspection of earth and infrastructure. That's a general category of all of the different uses. Gpr was first commercialized in 1970 by Geophysical Survey Systems, Inc. And it went digital. It was analog when it was first used commercially. And digital and 3D processing happened around 1999, the year 2000. LiDAR, on the other hand, also was commercialized around 1960, 1970, using stationary detectors. It went airborne after 2000, when a really accurate GPS system could be used on aircraft. Okay, Gpr is electromagnetic reflection, just as you would imagine it would be for airport radar. It uses an ultra-wideband frequency transmission, however, and I'll show you the difference between that and normal radar. It operates roughly in the area of 30 megahertz to 3 gigahertz, as it says. No one antenna covers this whole frequency spectrum. I'll show you, there's about 8 antennas required to cover this frequency spectrum. High frequencies give you more resolution but less depth. Low frequencies give less resolution in terms of the target, but a lot more depth. So this, I won't read all this to you. I'll let you read it yourself, but the radiated power is very, very low. As you can see, it's about 1% of a cell phone transmitter, and it's regulated by the FCC. So the secret sauce in ground penetrating radar is a very, very sensitive receiver. So these practical limits that I'm showing, the 30 inches in concrete is a very high frequency, high resolution antenna. And then as you go down deeper to 100 feet, it's very low end of the frequency range, large antennas. The 1,000 feet in ice, I'll show you that as one of the uses at the end of this lecture. This shows some of the different antennas. At the bottom down here are the really small antennas. They're the high frequency, high resolution antennas. Okay, I keep getting the, and then the larger antennas operate at lower frequencies and will go a lot deeper, but give less resolution in terms of seeing the targets. I'll note that the orange antenna, if you see an orange antenna, that's an antenna from GSSI. This shows the difference between a cell phone signal, as it's indicated there, which is very narrow band frequency, but high power, compared to the GPR signal, which covers a wide frequency spectrum. As an example, this is frequency across the bottom, as it says, relative power on a log scale on the y-axis. This power under this curve here, like I said, is 1% of a cell phone when you add it all up. A typical antenna, one antenna might range from 200 megahertz to 800 megahertz, producing a fairly uniform transmission signal. Here are some of the uses. There's about 20 different uses for GPR, archaeology being just one of the 20. I'm not going to read all these for you. I'll just highlight a couple. Highway inspection can be done at 60 miles an hour to make sure the highway pavement and concrete thickness, base and sub-base were built to specification. Much better than doing cores. Bridge inspection, you've heard about in the US, we have a lot of bridges that are deteriorating. The ground penetrating radar can look at the bridge deck and find corroding rebar, rusty rebar, compared to clean rebar. And the rusty rebar inside the concrete leads to potholes. Railroad bed inspection is another interesting one. I'm not going to cover it here. So here's 5 uses. We move it on. Some of the commercial applications, snow and ice thickness. The Canadian Coast Guard, as an example, looks at the ice thickness of the St. Lawrence River and to know when to send out the icebreakers in the wintertime. And they measure the ice thickness from a helicopter using a GPR. Forensics, I'll cover more of that a little bit later. Civil engineering, leaking pipes, you can see actually see the water leaking from an underground pipe. Other uses, military uses, finding tunnels, arms caches, graves. You can find microphones buried in concrete walls that are put in the walls when the building is constructed. Through-wall tracking of people is one of the new things I'll talk about toward the end. And unexploded ordnance detection. So any bombs or other smaller munitions that have landed in the ground that were unexploded can be found by GPR. Some of the unusual surveys, and I'm sure you've heard of a couple of these, that discovery of the woolly mammoth took place in about 2003, 2004. And that was quite a find in Siberia. The survey of an unopened tomb in Xi'an, there's a tomb about the same size as that terracotta warrior tomb that was opened 20 or 30 years ago. But it's a tomb that has not been touched. And our GPR found a lot of artifacts in it, so it's not been looted. So someday that will be, the Chinese will decide to open up and excavate that tomb. Down at the bottom, the last one, Iraq, Saddam's hiding place, we sold a number of units to the army who finally went over about 6 or 8 months after the invasion with a focus on finding him. Intelligence placed him in a particular farm villa area, and then the radar found his hidey hole and found him in it. This is what a typical system looks like. That's a 400 megahertz antenna that's on the ground between the wheels. It's orange in color when it's in color. The controller that the person is looking at, you can actually see the 2D radar penetration of the ground. So you see distance versus depth. And I'll show you that in what it actually looks like. So you can actually, as you walk, find hidey holes, tunnels, pipes, and mark them as you go. This is the highway survey equipment. As I said before, you can go down a highway at 60 miles an hour and measure the pavement thickness, base, sub-base, anything down to about 2 to 3 feet. This is a group of antennas called Terravision. There's about 8 antennas across the back of this unit for doing pipeline surveys, as it says. So you can run a mile or so or 2 miles along a proposed pipeline path and find all the crossing pipes, wires, conduit, whatever may be crossing. So when the pipeline people then dig the path, they'll know what to avoid, what to look for. This unit, very interestingly, to give you an idea of how powerful the software is, you can push one button at the end of this mile-long survey, and it will automatically show in 3D all of the pipes. So there's very little human intervention needed to find where the pipes are, the crossing pipes. This is a smaller unit that looks into concrete. I'm gonna, up here, you can see the mesh, in 3D that this unit found in this rooftop. So you can get quite detailed looking into concrete. And of course, this is for people that want to core cut or drill into concrete, installing fiber optics, installing drains, conduit, whatever else you might want to do. You don't want to hit some of the vital pieces, conduit or post-tension cables that may be in the concrete. Okay, this is what the 2D view looks like in real time. So when a person is walking, in this case, this is a parking lot deck of concrete. The depth is down the y-axis. Distance goes along the x-axis. So as it says there up here at the top, this is the surface of the concrete, the middle of the white band. The bottom of the concrete is the middle of the black band. So this concrete deck is about 14 inches thick. You can see the rebar. Each one of these hyperbolas shows where there's either rebar or part of the mesh that's in the parking lot concrete deck. So that's what you can see real time. Now, when you do a number of parallel lines, then you can get 3D in post-processing. So once you've collected 8 or 10 parallel lines, then you can go to 3D. And this is what a 3D wire mesh looks like from a bird's eye view looking down on it. The area covered here is 2 feet by 2 feet. And you can see the mesh overlapping. And this is this mesh overlapping is not to code. There should be a full square of overlap between mesh. And of course, once the concrete's poured, you can never see that unless you have ground penetrating radar. So this is shows the complete screen of what you can get. Over here on the left is a single pulse, a radar pulse that was, and the reflection shows here of a rebar up at the top here. So a single pulse, when you have many of those, then you get the 2D view over here. So this is a combination of pulses. So you get the 2D view. And when you have multiple 2Ds, then you get the 3D view, which you see here in the middle. This particular 2 foot by 2 foot survey was taken in a Japanese building in Tokyo, up on the 3rd or 4th floor during a demonstration of collecting data. And it just so happened this was the exact spot where there was electrical conduit, an electrical junction box sitting on top of the rebar. So you can see the yellow is the electrical junction box. The red pipes, a conduit going off in 4 directions, carries the electricity to various places, and it's sitting on top of the mesh that's in the concrete. All of this, of course, is without looking into destroying the floor at all. The floor can be covered with tile, carpet, whatever, and it doesn't matter. You can still see this in the concrete. Pretty interesting, the 3D views that you can see now. Here's a 3D view of a parking lot area looking through asphalt. And this survey, as it says at the bottom there, is about 52 feet by 16 feet. The distances are shown in meters. But there's 3 pipes. One shallow pipe here at about 1.5 feet deep. Another pipe, horizontal pipe, that's about 5 feet deep. And then there's a dipping pipe that goes down at an angle. And you can see where the radar sees it here and radar sees it here. Multiple horizontal slices through the data would show you more spots. But anyway, you draw in the pipes. So these horizontal slices through the data can be done at any location to get an idea of what's taking place at different depths. And you'll see more of that as we go through the data. Okay, on to archaeology, finally. I like this picture. It's of course taken at Petra. A French university survey team was taking GPR surveys in the area, and they parked their donkey with our GPR system. You can see the antenna here, and then the controllers in this box here. So unique transportation system for GPR at a very unique location. Here's what some of the data might look like. This was taken in Jordan. There's buried foundation. These are 2 horizontal slices through the data taken at different depths. So the survey on the slice on the left, it's the same survey. The slice on the left shows the foundation down deeper. The one on the right shows the remaining foundation at a higher level. So you can see the wall at the north end here is going to be taller. The wall underground, this is all underground. It's taller here than the walls that were here and here. So fewer stones were stolen, I guess, from the wall here. But this shows where the foundation is. So for archaeology, now then using GPR, you know exactly where to dig. Digging no longer needs to be random. It's a great aid in speeding up finding the correct places to dig. Okay, here's in Valencia, Spain, a 15th century church built after the Catholics regained all of Spain. The church was undergoing restoration, as you can see with the scaffolding on the left. And this is part of the colonnade that goes around the cloistered area, garden area. So this is this colonnade that we're looking at goes on all 4 sides of this enclosed cloistered outdoor area on the left. And the amazing thing was what was found there was buried in the cloistered area were tens of skeletons of people that apparently had died from one of the plagues in the 16th century. All of these people were buried without coffins. They were stacked, so apparently they were in a hurry to get them buried. You can see arms crossed, so somebody took care of them. The radar here was being used to identify where the bones were so they could do digging a little faster. They had a deadline in terms of the time they could spend in looking for the skeletons. So interesting use and find. This is very unique. Moving on to Italy, the Duomo in Florence. We were lucky to get the archaeology leader in Florence to let us into the basement of the church, which is not open to the public. And we did a 2D survey line that we're looking at here. So this is the floor. This white line is the floor of the basement. The depth is the y-axis down here. So these four white, essentially slabs, are graves that were the covering for graves. The interesting thing for this, and the reason I like to show it, is the archaeologist of Florence felt that this wall here was probably the wall of the Christian church that was there in 600 AD. The Duomo, built in the 14th century, was built on top of that church. So again, you can find all kinds of things underground without having to do any digging. Back to the US. This is George Mason's home, built and completed around 1759. George Mason was a fourth generation colonial and was a neighbor of George Washington. So his George Mason's plantation that we're and home that we're looking at here was just south of Mount Vernon on the Potomac River. And George Mason was heavily involved in the Declaration of Independence and the Constitution, and primarily in the Bill of Rights. That's a whole different history that's interesting to look at. But the question here was, there's a small walled-in area containing about 22 bodies that was George Mason and his wife and the close family. But there's a grass area all around it. And so the question was, is anybody buried outside this small walled area? So we did a Gpr survey, and here's, first of all, here's what graves look like. Two graves here on the left. The depth, as you can see over to the right to the top of the grave, is about 5 feet. So in all probability, a lot of land or dirt has been piled on top of this well after the burial. The grave on the right, the top of the grave is about 3 feet, which is probably about what it was at the time of the actual burial. And we're showing this blue-red highlights here. You can do a lot of things with the radar data to emphasize the higher returns from objects underground. So here's what we found down at the bottom here, where it says walled cemetery, is where George Mason, his wife, and about 20 close relatives were buried, and it was walled in by the DAR in the 1920s. But this whole area above that, and the area is looking at across the bottom here, it's about 100 feet by about 80 feet. So it's a large area. And it was all grass, except for these trees, and these green circles indicate the tree trunks, and pretty much a relative size of the tree trunk. But in this grass area with no markers whatsoever were all these graves. And this is only showing one side of the walled-in cemetery area. So these graves were on 3 sides. So there was over 100 unmarked graves that we were able to find with the radar. So no telling who was buried there because all the markers are long gone. One interesting thing to note is, there's an arrow here that says north is to the right. All these graves lie buried east-west. The deceased's feet were always toward the rising sun. So all the colonial era burials were done in this manner. So you know immediately the east-west orientation of the graves when you're looking at old grave areas. Moving on to another family graveyard. This was, again, a grassed-in area. There's 2 footstones over here, and that was the only markers that there's graves here at all. There's 6 of these stone pillars or concrete pillars that mark the graveyard area, but the family wanted to know how many graves were here. So we did a survey, and you can see the layout there with the red tape being a start-stop line, the yellow tapes being the parallel lines taken with the radar. So again, when you do a number of parallel lines, you can get a 3D view. So this is how the layout typically looks when collecting data. Here's what we found. The green vertical columns here represent the concrete posts that were in the ground. This horizontal slice through the data is only showing 3 graves because they were at considerably different depths. Moving the horizontal slice to a different depth, you could see the remaining graves. There were about 7 in total. So the 3D view is here. Over to the right is the 2D view of those same 3 graves that you can see. And you can see one smaller in the middle, then a larger one on the left. So this is a very typical graveyard situation where you can find the graves and mark them. Here's another interesting survey to show you what else you can find. This is a farmhouse built at the end of the 18th century on the Maryland's eastern shore. So on the Delmarva Peninsula, this farmhouse is there. And you can see this is grass area leading up to the house, totally grass. And this is the current driveway that runs to the left to the newly built garage. But so we surveyed this area right from the house down to the road. And the next screen shows you what we found. And this was rotated 90 degrees. So we were looking from down here toward the house. So here's the existing road that you can see. But what we found in the data down at about 6 to 12 inches is this compacted dirt road that ran up to the house, circular driveway in front of the house and back. And of course, all the horse-drawn carriages of the day, difficult to back up. So you always had a circular driveway in front of the house when you dropped off people or goods. So you could really see this old compacted dirt from 150 years earlier. It hasn't changed. And here apparently there's a foundation for a small little building, roughly 8 feet by 8 feet, that some steward or somebody waited for the horse-drawn carriages, I believe, but hard to say. But it's a foundation in the ground. And this is a drain pipe that runs from it to drain any water away from it. So the survey area is about 200 feet by 70 feet. So you can cover a pretty big area, but an interesting how much you can see below ground without digging up anything. Here's another one, a different one, a golf course green in Maryland. And this is in the area where New Providence, the town of New Providence was founded, the predecessor to the town of Annapolis, across the Severn River. Underneath this golf course green, the survey, again, is about 200 feet by 70 feet. Rather than show the radar data, I've just put in orange here. We found the foundation of a building that's about 10 feet by 20 feet, and another foundation about 6 feet, 7 feet by 7 feet. This dotted line here shows that there was, we found a footpath or a horse path alongside these 2 structures. So these are the foundations of the buildings, the building and the outbuilding. All of the walls are long gone, the stone's taken somewhere else. But under this golf course green, you can find 17th century foundations in the very early times of the state of Maryland. This, I show this one to show the results of what can be done when you're totally ignorant. These standing Buddhas were carved out of the cliffs in the 6th century. There were 2 of them. The Taliban didn't like them as the images, so the Taliban blew them away. So this is what it shows today with the older photograph on the left. Here with the radar is a Japanese team surveying and trying to find a reclining Buddha. Legend has it that there was Buddha built, carved out of the ground, out of the stone ground, that's been covered up, of course, over time. So they were trying to find that with the radar in the same location. So again, another interesting use of the radar. In Italy, the final one for archaeology, this was an Egyptian artifact brought back from Egypt and is now in an Italian museum. The man there is surveying the artifact to find places where it had been taken apart and glued back together a long, long time ago. So tried to find the old joints of where it was assembled. Okay, away from archaeology and on to a couple of other uses for GPR. You may or may not know that a road about 1,000 miles long was built from, as it says, from McMurdo Station to the South Pole in about 2000, 2005. Raytheon and the Army Corps of Engineers, the Coal Regions Environment Laboratory built the road. Here's what happens. There were a couple of crevice areas, by the way, along that 1,000-mile stretch. There were two major crevice areas. Crevices formed from deep down and worked their way up to the surface. So here's an Argentinian snowcat and a Chilean snowcat that crashed through the very thin surface ice and broke through. And you can see that that could be a major problem for the people involved. So the answer to this, of course, which the Raytheon and the Army Corps of Engineers used, was develop the snowcat, a leading snowcat that would then map where those crevices were. So as it says here, this 400 megahertz antenna, 200 megahertz antenna, would protect the snowcat and find any crevices near the surface. The antennas in the back, this is the transmitter, this is the receiver, could look down as much as 1,000 feet in ice. Ice is a good conductor for an electromagnetic wave. So this then would, the unit back here would map where the crevices are. So when you find the crevices, especially when you find a big one, here's, they dynamited this one open. And you can see that as this fell away into over time, this would be a huge crevice that somebody, a snowcat or a sled could fall into. So anyway, this was dynamited open, uncovered, and then of course marked. Another new application is detecting people buried in debris piles, you know, from earthquakes, terrorism, whatever may cause a building to collapse. So for search and rescue, it's been used in the China earthquake in about 2008, and then in the Haiti earthquake a few years later. So here's what the unit looks like, or I'm sorry, here's what breathing looks like behind a concrete wall using GPR. So again, this is time going across the x-axis. This is distance from the wall, or from the unit through the wall to the person about 4 feet on the other side of the wall. And so each one of these reversals here, blue, red, reversals, is the person breathing. Inhale, exhale gives a reversal. That's the motion of the chest. So over time, so as time passed, someone yelled at him, "Hold your breath." So this person behind the wall held his breath for about 7 or 8 seconds, took a deep breath here, as you can see, and then continued breathing. So you can see with a ground penetrating radar system, you can look through concrete reinforced walls and see people on the other side. So for search and rescue, a system was developed. Like I said, it was used in China and Haiti, where the antenna here can look through this concrete deck material. This location is a FEMA site north of Beverly, Massachusetts, where search and rescue people are trained. So this person that goes into the plastic sleeve here, the unit can pick him up and Wi-Fi or Bluetooth to the PDA held by the person doing the search and rescue. So to see what that PDA looks like, the person breathing only, could be in a coma, you get a red circle, and the depth, 4 feet in this case. A person moving, arms and legs, will get a black square, and again, you can see the depth to that person. Now, they're somewhere in the cone. You don't know the exact location within the cone, but you know that somebody's there. So you can find people through virtually anything except solid metal. The final interesting use is on a rover that's headed to Mars or been to Mars. The whole idea of using ground penetrating radar is to look for stream beds that have been buried by moving sand. So the common thread, as it says here, between life, climate, and resources is water. So if you can find sources of water where water used to be, that can lead to other excavations. So a couple of quickies here. There's some NASA people using an antenna on a cinder cone. Don't want to be the person up here dragging this, and you can see another person using a radar up here on the surface of this, on the top of the cinder cone. But anyway, they're testing the radar to see what it can do, how far it can go, how deep it can go. And here's a model of potential rover unit that would use GPR. In this case, the antennas would unfold because the antenna would be too big to have it go intact. But unfolding an antenna is not a problem. So radar is going to most of the planets, the moons. Here's my final slide. You can breathe a sigh of relief. And the reason I like this slide, it shows 2 people on Westminster Bridge in London looking through the concrete to find corroded metal. Now, it could be rebar, it could be the metal supports, but you can look into concrete on a bridge and you can, like I had said before, you can tell the difference between corroded metal, rusty metal, and clean. And if you have rusty metal over time, you've got to do something about it. The reason I like this picture so much is that up here on the face of Big Ben, you can see 2 people hung by ropes working on the face of Big Ben. So it's kind of a great photo that I liked, our equipment in use with people working on Big Ben in the background. So with that, that concludes my my lecture on GPR. I hope that you found some interesting things to think about and talk about. And GPR will continue to evolve in many different ways and many different uses. So thank you very much.